So here we are in chapter 6. Now, for those of you who are just kind of following along with the lectures and maybe didn't realize, we skipped chapter 5. Now, chapter 5 really digs into some more advanced topics of computer architecture and multimedia, which is an extremely math-intensive topic. So, chapter 6 gets us into performance, meaning, and metrics, which a lot of us probably understand maybe what performance means, but we're going to dig into that as an actual definition and really start to talk about how do we judge a computer? How do we decide if a computer is fast enough or faster than, and compare computers to each other? So getting started, the book starts us out with just this little dialogue, right? A little old man goes into a computer store. A sales assistant approaches him. He says, "Can I help you, sir?" And he's like, "Yes, I'm looking for a new computer." And the associate says, "You've come to the right place. Is there anything you're looking for in particular?" And he's like, "Yes, I want the one with a spec 2006 rating of better, or 350, and a total power dissipation of 150 watts. And I'd like a GPU with a rating of 1 teraflop. And, nobody talks about computers like this. You don't go shopping for computers like this. But, the joke here is the sales associate's like, "Oh, yes, would that be the one in the silver case or the one in the black, sir?" And so that's the joke, right? No one really talks about computer performance or shops for computers based on these kinds of specifications. But in this chapter, we're going to talk about kind of one of I think the most interesting, but also the most problematic topics in computer architecture, which is performance. And it's interesting because few people seem to agree on how to measure it or how to interpret the results. Now, it's problematic because, as this little story illustrates, it can be kind of incongruous in everyday situations, and also because performance specifies only one aspect of a computer, and it's maybe an aspect that's the least important in many applications. So a dictionary definition of performance is how successful something is or someone is, but there's a problem with this kind of definition because it's almost entirely useless. It simply replaces the word performance with the word successful, and that doesn't really give us any more information about what performance really is. And you might think that I'm being kind of deliberately obscure here, but everyone seems to think in the computing world that performance indicates speed. But really, we can think about it kind of like that, but not entirely. One computer performs better than another if it's faster, but it's not really as simple as that. And so if I have a PC that can execute a program more rapidly than, say, a little iPad, suppose we compare the performance of my PC with my iPad by running a utility such as a calendar. If we measure the time from switch on to reading the result, the iPad is going to be far faster because the PC has an intolerably long boot up period, whereas the iPad is going to spring into life so much faster from the moment it's switched on. And any advantage the PC has in terms of raw processing speed is lost in the delay, or what we would call latency, and that it experiences during initialization. So although this example is a little trite, it demonstrates that defining a computer's performance is far from simple. So in this section, this is what we're going to talk about. We're going to explain what we mean by performance and show how we can compare one computer with another, and introducing this concept of the benchmark. And this may be a concept that you're already familiar with. A lot of people use benchmarking tools these days to test out GPUs and video card performance. But benchmarking is really a program or a suite of programs used to compare one computer with another by measuring how long each computer takes to execute the benchmark. And an important objective of this chapter is to explain why computer performance is such a difficult and elusive notion. And really, we didn't even start talking about the subject of performance until recently. Because again, performance is not a simple concept, even today when we have computers that are far more powerful than when we first set out to start talking about performance. So we can think of a large organization that has to buy hundreds of thousands of computers for their banking empire that's going to be the most interested in getting the best deal for their money, and it needs objective criteria by which competing bids can be compared. And small office and home office computer users are a very different situation. What we're looking for in business is not necessarily what the home market is looking for. And they don't have a means to evaluate computers or interpret the results really. And I would even go so far as to say that the modern consumer who walks into a Micro Center or a Best Buy just is not equipped with the right information in order to judge computer performance accurately. So really, we think about performance as being important to those who run cutting-edge applications such as computer games and video applications. And because of this, popular computer magazines tend to lean towards the consumer and have defined their own standards for performance that are different from the more formal criteria that you would find in like commercial or academic type applications. And so the one thing that we really want to talk about, right, in this static world where we wouldn't need to think about performance, there would be little change from day to day, but we know technology is changing all the time, right? It's developing at a phenomenal rate. And so we start talking about this concept, right? We've talked about Moore's Law before, but Moore's Law is probably the most quoted and, in my view, the most misunderstood law of computing, because Moore's Law is not a law, right? It's an observation at best. But Gordon Moore was the director of Fairchild Semiconductor Research and Development Laboratories in the mid-1960s. And in 1965, he wrote what was to become a classic paper in electronics, which was a periodical at the time. So that paper was called Cramming More Components onto Integrated Circuits. And at the time, the integrated circuit was relatively new and the number of devices per chip was pretty minuscule. And so let's take a look at this example right here in this figure. This figure shows us that really because semiconductor devices were fabricated by photolithographic processes, that's a hard word. The circuit, right, is projected onto the chip, and then the chip is etched and it's heated and gases. All right, it's a pretty technical process. There's no direct relationship between the cost of manufacture and the number of devices on a chip. And so what Moore observed was the consequence of this manufacturing process is that the cost per device is inversely proportional to the number of devices. And so the cost of chip manufacture rises rapidly as the size of the individual chips increase. And really Moore made two observations. The first is that increasing the number of devices, which was transistors, per chip, forces the cost per device down until the size of the chip must be increased to accommodate extra devices, at which point the cost per device increases. So for any technology, and we're talking about manufacturing process, there's a minimum device cost. The second observation is that the march of technology is continually increasing, and the yield and maximum size of chips is going to continually increase, which means that the maximum number of devices per integrated circuit is increasing year by year, and the minimum cost per device is decreasing. And we've seen this, right? At this point, we've definitely seen this happen in the market. And what Moore suggested is that the maximum number of devices required to achieve a minimum cost would double every year. And although he changed the prediction to about every 2 years in 1975, really this is where we've found ourselves to be, right? And so the term Moore's Law was never used by Gordon Moore himself, but it was really coined by Carver Mead in 1970. There's really no precise formulation of what Moore's Law means, because again, it's not a law, it's an observation. But really what it talks about is this exponential increase in the number of components on a chip. And over time, Moore's law has come to imply a doubling in the performance of digital systems every 18 months. And really, the law, based on an observation of this progress of semiconductor technology over 4 decades, is a trend that we've continually seen kind of largely unbroken until we hit 2010. And this is something that is probably unique in human endeavor. So if a man in 1960 was sauntering along the street and he increased his speed in accordance with Moore's law, he would now be moving at 33,554,432 miles an hour in 2010, which is nearly 1,000 miles a second. And so it is actually quite an interesting observation and feat that we've managed to continue this pace. And really, when we look at this, it represents the triumph of a cyclical and multifaceted development process. And it's multifaceted because developments in all aspects of semiconductor technology are taking place. We have materials, we have purification, we have photolithography, we have X-ray, we have ion beam imaging, and it's cyclic because new advances make it possible to create more advances. And so, for example, the very first chips were designed and laid out by human engineers. Today, design, testing, layout, verification, it's all performed by computer-aided design. And again, Moore's law is not a law because Moore's observation has no basis in physics or the natural laws. It really should be renamed Moore's luck because it represents the longest winning streak in history for the fact that he made such an observation and then consequently it continued. But it is natural to ask and think about how long can this continue? Because clearly it's not going to go on infinitely because conventional semiconductor technology will soon reach the limits set by the atomic structure and the matter of limits set by quantum mechanics. And so this is where currents can no longer be considered to flow smoothly if we reach currents made up as a handful of electrons, right? We're literally coming up against the laws of physics. And already, and that's why we say up to 2010, already we've seen the maximum clock rates of processors begin to slow down as heat dissipation has become the biggest problem. It is the rising factor in why we've kind of slowed things down, as it's no longer possible to cool chips adequately. So I was showing you some of these graphics as I talked about this, but let's back up to this one, this figure 6.2. So this figure here displays the number of transistors per chip as a function of time. And you can see here in barely 5 decades, the chip density has gone from in the region of 2,000 to 2 billion devices, which is really hard for a human brain to even think about when we look at these microprocessor chips. So let's look at this one here, this figure 6.3, which describes the progress of Intel's mainstream microprocessors specifically. And this power is what, the Intel chip is what powers most of the world's personal computers. And the author talks about meeting an engineer from Intel at a conference who told him that Intel was so confident in the continuation of Moore's law in the medium future that they could begin the design of the next generation of microprocessors, even though at the time the required fabrication technology did not exist. And we're starting to see this in a lot of different types of advancements. And I think this is specific because I can talk about this right now. We're right at the beginning of the new year. And just a few weeks ago, we launched the James Webb Space Telescope, which is a project that's been in production for 20 years. And they actually set out with this idea of technology that hadn't been invented yet, that they knew they were going to have to develop in order to get here. And so this is not an uncommon type of plan. It's a very ambitious type of plan. But progress at this point is so reliable that engineers could assume that by the time the next generation of processors had been designed, suitable technologies would be in place. This is very similar data here in figure 6.4, but provides a 3D dimensional illustration of this growth of semiconductor technology by plotting both transistor density and the number of transistors per chip against time. And so you can really kind of visually get an idea of where we are. So when we look at the computer, the density of semiconductor memory has grown exponentially. And so of course we'd expect that because microprocessor and memory technology go hand in hand, we can see here in figure 6.5, it demonstrates the growth of DRAM memory capacity over the last 50 years. And DRAM is the mainstream memory component used to provide the bulk of main memory storage in PCs, right? This is like your DDR chip-based memory that you would put into your PC or your laptop. And it's able to store 1 bit of data per transistor. So in order for computer systems to reap the benefits of technological progress, it's necessary that progress take place across all components of the computer. So there's little point in making processors faster and faster if the data that they need cannot be read from memory or moved from place to place via the buses at a sufficient pace, right? You're just going to end up with bottlenecks and you're not going to see the type of progress that you should if that was being spread across multiple components. And so as we talk about this further, we'll see that progress is not uniform and that bottlenecks do develop because some technologies, such as hard disk transfer times, are lagging behind our processor technologies. And we'll also look at processor manufacturers and how they improve CPU organization in order to kind of help overcome these deficiencies and like almost pick up the slack or loosen those bottlenecks a little bit. And a good example of this is the introduction of multi-threaded processors that allow the CPU to switch to another stream of instruction if the current stream is stalled or waiting for some data from memory or from the hard disk. So, and just like the semiconductor and memory, personal computers and workstations currently rely on magnetic recording technologies and hard disk drives. I know we've gotten more into the solid state drives, which don't have the kind of latency that we saw in the spinning magnetic platters. But these devices, right, we've seen a dramatic increase in storage density, and we can see this here too in this figure that demonstrates how these have kind of increased over time, where we can now store more information in our computer. However, because of their mechanical nature that uses one or more spinning platters, which I know a lot of people these days, they have SSDs in their computers, but if you go buy a computer or go spec one out at like a Best Buy or a Micro Center or something like that, you'll often find that there's a mixture of solid state drives and traditional magnetic drives, simply to start to save costs, because those solid state drives are still quite expensive in comparison to our older technology. So the data access times and the data transfer rates of those hard disks have really not changed since their introduction. And I mean, we're really good at making them at this point, but it's kind of an interesting demonstration of the progress of disk technology in terms of kind of our year-on-year incremental improvement as a function of price, which we can see here in this graph. So before we really look at how performance is measured, we need to emphasize that the performance of a computer is not dependent only on its central processing unit, but on other components of the computer itself. We have to look at it as a holistic system. And although this statement is largely self-evident, we have to make it because so much of the glamour of computers has been focused on the CPU. And we've all seen, like if you've gone out and bought a computer, that little Intel Inside sticker on laptops that stresses CPU performance, but no one has ever seen some like part number sticker or something like that on the outside of the computer, right? Like I know sometimes on gaming PCs and stuff, we see like stickers about the RAM or the video cards, but that is not typical. And so let's talk about some of the elements of a computer that determine its performance. And first we have to start with a question, because when we talk about performance, we really have to talk about who is interested in computer performance. Because we think about designers, engineers, academics, marketing people, right? performance means different things to different people. It means different things to the people who work on computers, and it means different things to people who use computers for their job. So we have to think about this. We have to take this into account when we talk about performance, right? The metrics that define a computer's performance are used by the designer to improve the computer's architecture and organization by doing things like locating bottlenecks and eliminating them or minimizing their effects. But the folks in marketing and sales, right, that hawk the computer, they don't want fancy benchmarks because, again, and I'm not trying to talk down about anybody, but the modern consumer is not prepared to judge or accurately think about computer hardware unless they've been through or are maybe like in the computer field, right? If you're a computer scientist, if you're a software developer, maybe if you work in like video or graphics design, where you've actually had to think about the internal components of your computer from that standpoint, right? All those folks want is a number that's bigger than the competitors, right? Or higher than the competitors or faster than the competitors. That's all that people in marketing and sales want. And so the shareholders, they've never heard of a benchmark. They do know a dividend when they see it. And so the end user, they just want value for money. And while some of our end users, again, depending on what they're doing with the computer, are looking for specific things, really the structure of a typical PC from the point of view of the systems designer is very different from how many other people who are involved or who might buy it or use it think about performance. So real computers range in complexity from a single chip controller in a point and shoot camera to a complex parallel system with multiple processors and distributed resources. And the performance of a computer is dependent on factors like cache memory, right? That's that fast memory that holds frequently used data, main memory that holds programs and data, buses that allow for the submodules to communicate with each other, and secondary storage, such as our hard disks and CD-ROM drives. Now, I know right now some of you are screaming because you're like, you're not talking about the GPU, the video card. That's also part of performance. I want my computer to be able to play games. But honestly, we don't start to talk about GPUs and multimedia from a systems architecture standpoint unless we go back to how we use multimedia, again, which is a very math-intensive topic on how processors actually move that kind of data. But from a systems architecture standpoint, unless you're actually talking about writing games, we don't talk about GPUs. So let's look at this figure here, figure 6.8, which shows the structure of a typical PC from the point of view of the systems designer. And what this demonstrates is that improved computer performance can come from many sources. And indeed, this figure only hints at some of these sources, because below the level of the CPU, the device physicist and the semiconductor engineer can create intrinsically faster devices. So, for example, the maximum clock rate could be increased by reducing the propagation delay of signals through the gates in the chip. And remember, I said today, heat dissipation is one of the principal limiting factors on computer speed. The heat density, which is watts per cubic centimeter, in a modern high-speed processor chip now approaches the same level as the heat density of the core of a nuclear reactor. And I'm not being facetious. This statement is true, but not quite as awesome as it seems, because these chips are relatively small and the total heat dissipated by a powerful CPU is in the order of 100 watts. And so some of you, if you're very savvy, have maybe built your own computer, you've had to think about CPU cooling, you know, or have maybe thought about overclocking your CPU, which then you really have to start taking heat into consideration because you're running the clock faster than the manufacturer's intended limits, which makes heat a bigger problem. And so maybe you've thought about this, or you know what temperature your processor is supposed to run at, and you have struggled with this on a personal level. And, you know, we have a lot of different cooling systems now, too, to try to help with this problem. We have really implemented, like, copper-based systems, multiple fans, ways to move that heat away from the die of the chip. You've probably heard of water-cooled based systems, right? There's lots of different ways that we've tried to solve this problem. So above this level of the CPU, we have the software engineer who develops compiler technology to better exploit the underlying architecture of the processor. And indeed, in today's world, the computer designer and the compiler writer have to work hand in hand in order to really make this the most efficient relationship. And then the issue of performance can sometimes be positively surreal. So for example, maybe you've seen published benchmarks for motherboards where the speed of the batch of boards being tested varies over a range of 1 to 2%. And such tiny variations can become meaningless in the face of factors such as cache memory that have a much greater effect on performance. Clearly, there's no point in spending a lot of time choosing between board A and board B on the basis of performance if there's little difference between them, right? And we could also debate the relative merits of some technologies maybe that we don't even really use anymore, like SCSI versus IDE bus adapters, right? Most of us have no idea what we're talking about unless maybe you're as old as I am and actually ever used a SCSI drive. But between computer systems in a hard disk drive, right, the performance probably doesn't matter. And the speed of those bus interfaces may be so much greater than the speed of the hard disk drives connected to them that even moderate variations in the characteristics of the interface have very little effect on the overall system performance. So it's easy to say that the designer should optimize performance, or like what the designer should do, right? But in the real world, the designer doesn't normally have kind of carte blanche to create an entirely new system. The computer is invariably part of a manufacturer's product line. It has to be backwards compatible with the code of previous products of the same family. And moreover, the computer has to work with existing software over which the designer may have no control. And the processor has to operate with other components such as memory and system buses, and you can't just optimize to suit your CPU, right? We have to think of it as a whole system. And then there's one final design constraint that it's like we don't normally mention it in polite society, but the processor will be interfaced to a bus or memory that could be covered by a patent. And so if you make the wrong design decision, here's Mr. Intel's lawyer, knock, 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 clutching a patent, who now is maybe wanting some money. And so it's definitely something we have to consider. So now that we've talked about what really is performance, how can we think about performance and kind of all of the factors, let's talk about how we compare the performance of various computers, right? And I'm going to state right here before we talk about this that computer metrics can be notoriously unreliable. We begin by introducing some new terminology of performance and then demonstrate why clock frequency alone is not a reliable indicator of performance. There's a really great quote by William Thomason, who was a British scientist that died in the early 1900s. But he did a lot of work on transmission lines that underpin kind of all of modern electronics. And he later became Lord Kelvin. I don't know if maybe you've ever heard that name, but here's the quote. When you can measure that you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the state of science. And so this is extremely apt when we apply this to performance. We need numbers to measure performance. But what numbers? How do we interpret these numbers? So let's talk about David Lilha. He provides a list of criteria by which we can judge the metrics of computer performance. Linearity, reliability, repeatability, ease of measurement, consistency, and independence. So we're going to talk about each one of these terms and what they mean so that we can start to understand kind of where we are with the numbers. Linearity suggests that a metric should be linear. So it's increasing the performance of a computer by a fraction of x should be reflected by an increase of fraction x in the metric. So if computer A has a metric of, say, 200, and it doesn't matter right now what we're talking about, and it is twice as fast as computer B, then computer B's metric, right, should be 100. And don't worry about what we're talking about yet. Like, you're like, 200 what? Just, that's what we're talking about when we say linearity. And we realize, right, that not all metrics are linear. And some good examples of this are like the Richter scale for earthquakes, the level of sound intensity, which is decibels, or camera aperture, which is f-stops, right? Those are all logarithmic. But since computer performance is increasing year by year at an exponential rate, then performance should be expressed in a logarithmic fashion. However, this is the criteria by which the industry has decided that we're going to use. Now, performance metrics should be reliable and correctly indicate whether one computer is faster than another, right? And we call this property monoticity. And so this is an increase in the value of a metric, which should indicate an increase in the speed of the computer and never vice versa. And this isn't true of all metrics. So sometimes a computer may have a metric implying a higher level of performance than another computer when its performance is worse. This situation arises when there's a poor relationship between what the metric actually measures and the way in which a computer operates. And when we talk about clock rate and MIPS, the instruction execution rate, they're two notoriously unreliable metrics. Now, a good metric should also be repeatable, right? And that probably feels really intuitive because we want to always yield the same result under the same conditions. Not all computer systems are deterministic, which means they respond in the same way to the same data, because the number of parameters that affect a computer's performance is very large, and indeed, we can't always achieve the same results of each test run in a program. If this seems hard to believe, then let's consider the following. Suppose you're carrying out a test that requires the reading of data from a disk. In the first run, the data might be about to fall under the read head at the time that it's required. Now, if you are not familiar with what a physical platter-based system looks like, maybe you could picture, I'm trying to think of maybe something you've seen before. I always lean on record players. I guess most people probably have seen a record player. But you have the disc, right? And then you have a head that reads off the top of that disc, right? So you can think of like a traditional record player. That's basically what these platter-based hard drives look like. And I definitely recommend that you go look up some pictures online if this is not helping follow. But let's suppose that the data that we're trying to test falls right under the read head at the time that it's required. And so the data read will be immediately ready. So in the next time that we run the same test, maybe the data just passed under the read head and the system has to wait for a complete rotation to access the data. And in the third run, the data is cached in RAM. So we entirely bypass the disk's hardware. And so consequently, in this example, we could have 3 very different metrics using the same data and yield 3 very different results. So the ease of measurement criterion, I always think is very self-explanatory. If it's difficult to measure a performance criterion, few users are likely to make that measurement. And moreover, if a metric is difficult to measure, an independent tester will have a great difficulty in confirming it. So it should be easy to measure a metric. And then a metric is consistent if it's precisely defined and can be applied across different systems, because it doesn't make any sense if we have a metric that we can't use on multiple systems in order to make a comparison. So this idea of a metric maybe being called having a universality or a generality, to avoid confusion with repeatability. I mean, these are just words. But really what we're talking about is consistency, which can be difficult to achieve. So if the metric measures a feature of a specific processor, or that feature is not consistent across all platforms, or it's using a clock rate as a metric and demonstrates a lack of consistency because the relationship between clock rate and performance is not consistent across different platforms, that's what we're talking about, right? When we talk about kind of this consistency. So a good example of this is the performance of a PowerPC processor is not the same as the corresponding relationship between the clock rate and a Core i7 processor. And so an example of a consistent metric that was commonly used to indicate the performance of graphic cards in PCs in like the late 1990s was the maximum number of frames per second at which the Quake game could refresh the display. And so I think that's a great example of kind of what we're trying to talk about. And finally, the last one that Lilha states was a good metric. It should be independent of commercial influences. And maybe this is kind of self-explanatory too, but if a computer manufacturer can define performance metrics, then they might be tempted to select a criterion that shows their processor in a better light than their competitors' processors. So in particular, if we have a manufacturer, right, and they might select a metric that emphasizes a specific feature of their processor that's lacking in competitors' devices, and even though this feature may have little to no overall effect on system performance, right, then we would have an issue where we aren't able to make a correct comparison. So independent of commercial influences is maybe pretty self-explanatory. So having thought about these different ideas of what makes a good metric, let's talk about some of the terminology, because computer performance has some characteristic terminology and we need to define a few of these terms so that you are clear on kind of what we're trying to talk about. So the first one we're going to talk about is efficiency. So a computer is always executing instructions unless it's in a halt state or a suspend state. However, the computer may not be always executing something useful, like an application level instruction, or it could be repeatedly going around a polling loop waiting for data from a peripheral, where we're waiting for other tasks to be executed, right? So the efficiency of a computer is an indication of the fraction of time that it's doing useful work, right? And we can take a look at this equation here that gives us what we're actually talking about for efficiency, right? And this example. So if a computer takes 20 seconds to perform a computational task and 5 seconds is taken waiting for a disk that's been idle to spin up to speed, then the efficiency is 20 seconds over 20 seconds plus 5 seconds, which equals 20 over 25, which gives us 80%. Next, throughput. The throughput of a computer is a measure of the amount of work that it performs per unit of time. So a bus's throughput is measured in megabits, whereas a computer's throughput is measured in instructions per second. The upper limit to a system's throughput can normally be determined from basic system parameters. So, for example, if a computer has 500 megahertz on its clock and it can be executed up to 2 instructions in parallel per clock cycle, and each instruction takes 1, 2, or 4 clock cycles, then the upper limit on throughput occurs when all instructions are being executed in parallel in one cycle, right? So that's 10 to the 9 instructions. And so we're assuming, in this case, that the best a computer can do is 1 instruction per cycle. And we know about multi-threading, and we maybe know about superscalar processors that employ instruction level parallelism and stuff like that. But right now we're just talking about things in a very simplistic way so that we can understand these terms better. And note that the definition of throughput includes the term amount of work, because instruction execution is meaningful only if the instructions are performing useful calculations. So a computer executing an endless stream of NOPs, which is no operations, may be operating at its peak rate, but it's achieving nothing other than to wait. So like, let's say you were working on your computer and you were writing something, but you went to take a break. You just left the computer. It's just sitting there, right? That's what we're talking about. If it's just sitting there waiting, then that's not useful instruction or calculation. So we'll see what instructions or why instructions per second is a very poor indicator when we actually start talking about performance of a computer. Next, we have latency. And we've used this term before. Latency is the delay between activating a process. So if we're starting a memory write or a disk read or a bus transaction and the start of the actual operation. So latency is that waiting time while we're waiting for something to give us what we want or be available so that we can do the action that we're wanting to do. And this is an important consideration in the design of rotating disk memory systems where we may have to wait on average of half a revolution for data to come under the read head. And in some computer applications, that affects the latency. That might be negligible in comparison with processing time, but in other systems, the effects of latency can have an important effect on system performance. And again, that goes back to why we're starting to see these solid state drives, which have this faster read and write time, right? Less latency, better access. But because they're more expensive, we're not seeing sometimes where computers are using them primarily for their hard disk storage. We're seeing a mix. So maybe you put your operating system like Windows and any real high intense applications on your solid state drive, and then you use the cheaper memory disk, physical disk for file storage and things that you maybe don't care so much about access time. And so, if you can afford to put storage into your computer that's faster all the way across the board, then of course you're going to get better performance. But ultimately, that's why we're starting to see that trend. Now, in some metrics and some benchmarks, they actually define latency as the time to finish a process, but that is not typically the accepted definition for how we should use latency. Then we have relative performance. So if we're interested in how one computer performs with respect to another, then relative performance is kind of the inverse of the execution times. So we can look at this equation here and give us an example. So if system A executes a program at 105 seconds and system B executes the same program in 125 seconds, we can calculate the relative performance as 125 over 105, which is 1.190. And so we could say that machine A is 19% faster than B, right? So when we talk about relative performance, basically how we can compare two computers that we want to kind of judge the performance versus execution time. And really, the objective of the computer's designer is to create a system with the greatest possible throughput. And so when we're trying to improve a system, this is where this relative performance comes in, because we're often most interested in how much better a new system is in comparison with an old system. So this is where we can start to use this relative performance speed up ratio. So here's an example. If our reference machine takes 100 seconds to run a program and then our test machine takes 50 seconds, our speed up ratio is 100 over 50, which gives us 2. Then we can look at time and rate. Benchmarks can be expressed as the time required to execute a task or as the rate in which tasks are executed. So one benchmark might yield a time of 20 seconds, whereas another benchmark might yield a rate of 12 tasks per second. So going back to the computer game Quake, which if you've never played it is quite an iconic game, it's become a popular benchmark for PCs, with the figure of merit being the rate in which frames are displayed by the processor. And although the Quake frame rate is probably a reasonable indication of how a computer performs relative to other computers running Quake, it's not a good general benchmark. They say people feel more comfortable with metrics that increase numerically with performance, right, as rates, rather than those that reduce with performance, which would be time. So this is the end of our part 1 for chapter 6, where we've talked about some of the terminology, about how we can talk about performance, some of the meanings and metrics. And so in the next section, we'll start to dig into clock rate and some of the things that we can look at when we're talking about computer performance.